My name is Martin Rees. I'm a professor at Cambridge University and my speciality is astronomy and space science. Welcome to my exp. I'm an astronomer and I think there are 4 reasons we do astronomy. The first is simply exploration, to find out what's out there. The second is to try and make sense of what we see, to try and understand it in terms of the laws of physics, and to perhaps discover some new laws of physics. The third is to try to understand cosmic evolution, to understand was there a beginning? If there was, how have things evolved from that beginning to the amazing cosmos we see around us and are a part of. And I suppose that leads to a final reason, the mystery of why things exist and why the universe is the way it is. So all these things are part of astronomy and what I do. And of course, pure thought doesn't get you very far, but thanks to improved instruments, we've made huge progress. And I would say that the last 50 years of astronomy have been one of the real highlights of science, up there with the standard model of particle physics, the double helix and all that. So I've been privileged to be part of this huge cosmic exploration. Astronomy is really a story of expanding horizons. To the ancients, the Earth was the centre and the Sun and planets orbited around. Post-Copernicus, we realise that we are part of a planetary system orbiting the Sun. We've now realised that there are many, many other planetary systems orbiting other stars, and that our Sun is just one of literally billions of stars in our galaxy, and that our galaxy is just one of many billions of galaxies that can be seen through a large telescope. And we've realised that our entire universe is a dynamic entity. Everything started off very compressed and compact, and it expanded, starting about 13.8 billion years ago, and it's gradually cooled down. Stars and galaxies have emerged, and we're coming to understand how this happened. Indeed, when I was starting my research about 50 years ago, it wasn't clear that there was a beginning, because there was a rival theory called the steady-state theory, according to which our universe had existed, as it were, from everlasting to everlasting, and although it was expanding, new galaxies formed in the gaps, as it were, as the old ones moved apart. That theory was certainly tenable until 50 years ago, and then 2 things happened. First, it became possible to look at objects so far away that we were looking back billions of years into the past. And in the steady-state theory, things would have looked the same there as now, but it was clear that the galaxies were different far away and therefore far back in time than now. So the universe and the things in it were evolving. And then even more important, evidence was found that the entire universe is full of microwave radiation coming from all directions, which can't be understood except as the afterglow of the hot beginning of the universe. The universe started off very hot and dense, it expanded and cooled, but this radiation is still around, it fills the universe, it's got nowhere else to go. And this is really unambiguous evidence that the universe had a hot, dense beginning. And later data pinned down the time of that as about 13.8 billion years ago. One thing we're trying to do is to understand how the universe evolved from that beginning to its present stage, how the first galaxies formed, how the first stars formed, and can we understand why galaxies have the properties they do and why stars evolve as they do. So that's really what we are trying to do. And I would add that one of the most exciting developments in the last 20 years has been the definite realization that our solar system is not unique. Most of the stars in the sky are other suns, and they have orbiting around them a retinue of planets, just as the Sun has the Earth and the other familiar planets orbiting around it. So this is an exciting new subject, and unfortunately, these planets orbiting other stars are so faint that we can't really see them with existing instruments. But with the next generation of telescopes, we'll actually be able to study the light from planets orbiting other stars. And this, of course, leads to the most exciting question, which everyone asks me when they know I'm an astronomer, which is there life out there? We'd like to know if on these planets around other stars there could be life, vegetation, even intelligent life. It's worth a search, and within 10 years I think we will know whether some of these planets, rather like the Earth, orbiting other stars, rather like the Sun, have vegetation and oxygen in atmospheres and other indicators that there's been biological evolution. At the moment, of course, we only know that life exists in one place, but if we could find it in a few nearby planets around other stars, that would tell us that the entire universe must be teeming with life, and that would be the most fascinating discovery of all time almost. I've been part of a collective enterprise over the last 50 years trying to understand what telescopes, which are ever more powerful and varied, tell us and try to make sense of it. And one thing which has made great progress is understanding the early stages of the universe. We can say what the universe was like when it had been expanding just for a few seconds. We can say that because at that time its temperature would be about 10 billion degrees, and that's a temperature where nuclear reactions occur, turning hydrogen into helium and deuterium and other substances. And one of the triumphs of our understanding is that the proportions of those atoms which we predict, if they were made in the Big Bang, agree with what's observed. So we have corroboration of the Big Bang right back to when the universe was a second old. But we'd like to go back further still, because there are many mysteries still. In particular, we don't know why the universe is expanding the way it is. We don't know why it's got the mixture of things in it. It's got some radiation, it's got some atoms, it's also got some mysterious stuff we call dark matter. And we'd like to understand this. And all of us agree, I think, that the answer to those questions requires us to understand not just the first second, but the first tiny, tiny fraction of a second. And the problem there is that if we imagine extrapolating back closer and closer to the original instant, everything gets denser and hotter and the physics more extreme. And for the first nanosecond, the physics is far more extreme than anything we can simulate in the lab, even in a big machine like the particle accelerator at CERN in Geneva. What we're aiming to do is to understand the galaxies and the stars in them. And we've now got a pretty good understanding of stars. Stars are really gravitationally confined nuclear reactors. They're very massive, so gravity holds them together. They're very hot in the center, and nuclear fusion reactions go on inside stars. And stars gradually burn their hydrogen to helium, and then they burn their helium further up the periodic table, etc. And we can understand this. And stars eventually die. The sun has been shining for 4.5 billion years, but after another 6 billion years, it'll run out of fuel, and it'll then blow off its outer layers and settle down as a white dwarf star. Heavier stars burn their fuel more rapidly, and therefore face an energy crisis earlier on, and then they explode. They leave behind a dense remnant, a neutron star or black hole, and blow off their outer layers. And this is something which you might think is entirely recondite and irrelevant to us, but is crucial for our existence. And to illustrate this, one of the most amazing objects in the sky is something called the Crab Nebula, which is expanding debris from a star which exploded in the year 1054 AD, nearly 1,000 years ago. This exploding star was witnessed and recorded by the Chinese court astronomer, I guess the counterpart of the Astronomer Royal, who reported to the Chinese emperor that a guest star had appeared and became brighter than the moon and faded after a few weeks. At that place in the sky, we see this expanding, glowing debris of the remnants of the star. Now, why is that relevant to us? The answer is we wouldn't be here were it not for things like the Crab Nebula. Because before a star explodes to make something like that, it turns hydrogen to helium, and then it turns helium into carbon, carbon to oxygen, oxygen to iron, etc. So before the star explodes, it's got a sort of onion skin structure where the inner parts are processed higher up the periodic table. And then, when it explodes, it flings out this material, which, even if the star started off with just hydrogen in it, would end up with all these elements. And this debris will eventually merge with the interstellar gas. And then it'll form new stars. So we can calculate that when a massive star explodes, it flings back into space gas which has all the chemical elements in it. And that is how the chemical elements in our universe are made. And then new stars condense from those. So when we look at our solar system, it contains all the atoms like oxygen, carbon and iron, etc., that we are made of. And it makes us feel an intimate part of the universe when we realize that every atom in our bodies was forged in an ancient star which lived and died before our solar system formed, which lived and died maybe 5 billion years ago. And then our sun and our planets condensed from gas contaminated by the debris from earlier generations of stars. So we understand that we are literally the ashes of long-dead stars, or if you're less romantic, we are the nuclear waste from the fuel that made stars shine. And this theory, which dates back to the 1950s, is really one which is one of the great achievements. I would put that up on the level with Darwin, to understand how we and all the chemical elements were made in stars. We have had, over the last 40 years, a fairly good theory for how the particles which make up the atoms around us were made and how they interact with each other. And sometimes you can make a prediction which is very, very hard to check. And in particular, there was a particle called the Higgs boson, which was a crucial sort of capstone of a theory of particle physics. And this was predicted by several people in the 1960s, but it took nearly 50 years before we had instruments powerful enough to detect it. And that corroborated the theory. And there are many other examples like that of things we are predicting now which can't be tested until we have a more powerful generation of telescopes. And in particular, those that excite me most are going to be telescopes able to look for evidence of life on planets orbiting other stars. This requires a very sensitive telescope, and it will be crucially important to see if life does exist elsewhere. Because as far as we know now, life could be unique to the Earth. We could be such a special place that life doesn't exist elsewhere. But on the other hand, if we can find evidence of life which had emerged independently somewhere else, maybe even in our own solar system, but probably on a planet around another star, then that will tell us that life is a crucial feature of our universe. And our universe, the starry sky, is far more complex and fascinating than the ancients thought. To make a final point, there's a distinction between the universe we can observe and the entirety of physical reality. And one of the most fascinating questions to me is how much bigger is physical reality than the region we can observe with our telescopes. I think everyone thinks it's very, very much bigger. The aftermath of our Big Bang extends far further than our telescopes can reach. And more than that, there's an important new idea called the multiverse, which is that our Big Bang is not the only one. There may have been many Big Bangs, each leading to a cosmos, maybe fully the equal of what we can see, And then the other question, which is crucial, is whether the physical laws governing these other cosmoses is the same as the laws governing ours. That's a fascinating question. So even though it's good for astronomy that the laws of nature are the same in all the regions we can observe, it could be that on this hugely grander perspective, this fourth Copernican revolution, where we have not just many galaxies but many big bangs, that the laws of nature display a huge variety.